Good morning and welcome again. We continue with our discussion on differential geometry of surface patches. This is lecture number 34. Let's talk about curves on a surface patch. This is a typical surface patch given by a vector function r of u and v, the two parameters. And let's say we have a curve on it. Now this curve is represented by c of t. Let's compute the tangent to this curve at any point. The tangent is given by total c over total t. C is a function of u and v here. Using the chain rule, we have partial of r of u and v over partial of u times du over dt plus partial r over partial v times dv over dt. You can do the math and you can express this right hand side as a multiplication of two matrices, a row matrix and a column matrix. This row matrix comprises of the tangent along the u direction, the tangent along the v direction. R sub u is given by partial r over partial u. R sub v is given by partial r over partial v. And then in the column, you'll have du over dt and dv over dt. You can think of writing this row vector as bold A, and then we have this column vector right here. In terms of scalar functions, x, y, and z, where each function x, y, and z is dependent on the parameters u and v, we can write A as partial x over partial u, partial x over partial v. That's in the first row. In the second row, we have partial y over partial u, partial y over partial v, and in the last row, partial z over partial u and partial z over partial v. This is not surprising because both these tangents r sub u and r sub v are vectors, and these are the components of these vectors. So this column here are components of ru, and this column right here are the components of rv. Let's now compute the differential arc length ds over a portion of this curve. Now ds is given by the absolute value of total c over total t times dt. Now dc over dt can be written as r sub u times du over dt plus r sub v times dv over dt. And then we have this dt here. Instead of using the modulus sign, I can replace this expression by this one here, the radical sign. And remember, this is a vector. So what we are doing is we are dotting this vector by itself. So within the radical sign, we have r sub u du over dt plus r sub v dv over dt dotted with itself. we can write this result in the matrix form here. If you look at this expression, this can be written as the row matrix du over dt, dv over dt times the column matrix ru rv dotted with ru rv times du over dt, dv over dt times dt. I can compute the dot product now. So we have ds equals, within the radical sign, the row matrix du over dt, dv over dt times this 2 by 2 matrix here now, whose elements are ru dotted with ru, ru dotted with rv, rv dotted with ru, and rv dotted with rv. And then we have this column matrix du over dt, dv over dt. This 2 by 2 matrix has a special name and accordingly a special significance. We'll come to that. What I would request you is to remember this expression or this matrix. We write that 2 by 2 matrix in short as capital G in bold. The rest of the expressions, they remain there. As I said, G is this 2 by 2 matrix with ru dotted with ru, ru dotted with rv, rv dotted with ru, rv dotted with rv as 4 elements. Recall from our previous discussion what A was. In terms of A, G can be written as A transpose A. Let me take you to where we describe A. So this matrix A is the components of Ru arranged in the first column and the components of R sub V arranged in the second column. If you realize G is a symmetric 2 by 2 matrix and it is called the first fundamental matrix of the surface. The definition of G is related in this slide to the infinitesimal arc length ds along the curve CT. We will now see certain properties of G. One of the properties that I had mentioned is that G is symmetric. Well, let's talk about the unit tangent bold T to the curve. The unit tangent T is given as partial R over partial U, which is R sub U in short, times du over dt plus partial R over partial V times dV over dt over the absolute value or the modulus of this vector. From before, we had seen that the modulus of R sub U du over dt plus R sub V dV over dt is given as square root of du over dt, dV over dt, this row matrix times G that we have defined in the previous slide, times du over dt, dv over dt. And we retain this numerator right here. To compute the unit tangent, we have to ensure that the denominator, in particular this expression here, should be non-zero and it should be positive. That is, for the unit tangent t to exist at any point on the curve c of t on a surface patch, bold G should always be positive definite. Well, what do I mean by a positive definite matrix? Say we have a square matrix of size n by n, and this matrix has elements A, I, J. In the expanded form, I can write this matrix as A11, A12, A13 up till A1n, A21, A22, A23 up till A2n, and the nth row as AN1, AN2, AN3, ANn. For this matrix to be positive definite, we have certain conditions. Conditions for positive definiteness. All principal minors have to be greater than 0. Now, what are principal minors? They are the set of determinants that you construct from this matrix. For example, the first principal minor will simply be the first element A11. The second principal minor will be the determinant of this 2 by 2 matrix. If I write the third row here, the third principal minor, N3, will be the determinant of this 3 by 3 matrix. A11, A12, A13, A21, A22, A23, A31, A32, A33. In short, it's written as D here. We can continue until the last principal minor, Mn, which is the determinant of the matrix itself. Alternatively, we can also describe positive definiteness of the n by n squared matrix in terms of its eigenvalues. If I write the eigenvalues of this matrix as a set EIG of A, then A is positive definite if all eigenvalues of A are strictly positive. If some of them are equal to 0, then we call A to be positive semi-definite. If some of the eigenvalues are negative, then A is not positive definite. Let's come back to where we were. We had said that for a unit tangent T to exist on a curve, the matrix G, the first fundamental matrix, should always be positive definite. The first principal minor, G11, as you know, is given by R sub u dotted with R sub u. And for R sub u not equal to 0, this dot product is always greater than 0. So the first principal minor of G is positive. The second principal minor is given by the determinant of G itself, which is G11, G22 minus G12 times G21. The first element, the fourth element, the second element in the first row, and the first element in the second row. In terms of its constituents, determinant of G is Ru dotted with Ru times Rv dotted with Rv minus Ru dotted with Rv squared. One can do a bit of algebra to figure that this expression is nothing but Ru crossed with Rv dotted with itself. And we have seen that Ru crossed with Rv is the normal to a curve and therefore to a surface patch at that point. The dot product of the normal with itself has to be greater than 0. And since the first two and the only two principal minors of G are greater than 0, G is in fact positive definite. So the length of the curve segment for parameter values t in between t sub 0 and t sub 1 is given as S equals integration from t sub 0 to t sub 1 of ds, which is equal to integration from these two limits t0 to t1 of the square root of du dt, dv dt, the row matrix, times the first fundamental matrix G times the column vector du over dt, dv over dt times dt. So this dt appears outside this square root sign. Let's say we have two curves, C as a function of some parameter t sub 1 and another one C as a function of parameter t2, which is different from t1. And these two curves lie on the surface patch R of u and v. And let these two curves intersect at angle theta. This angle is given by the dot product between the two local tangents. T1 dotted with T2, which is equal to partial r over partial u times du over dt1 plus partial r over partial v times dv over dt1 over the square root of du over dt1 dv over dt1 times g times du over dt1 dv over dt1 arranged in a column. So here parameters u and v are assumed to be functions of parameter t1 respectively. Likewise, the second tangent t sub 2 is given by r sub u times du over dt2 plus r sub v times dv over dt2 over the square root of du over dt2 dv over dt2 times g, and in this column we have du over dt2 dv over dt2. And since t sub 1 and t sub 2 are unit tangents, this dot product is simply the angle, rather the cosine of the angle between them. Let me copy the previous result here. Now let's say if u is parameter t1 itself and if v is parameter t2 itself, then t1 dotted with t2 is given by r sub u dotted with r sub v over the square root of ru dotted with ru times the square root of rv dotted with rv. You can verify this. If u equals t1, this expression is 1. If v is equal to t2, t1 and t2 are independent parameters, so this result is going to be 0. Likewise, this result is going to be 0 because u is t1 and dt2 over dt2 where v is t2 will be 1. So in the numerator we'll have r sub u, this expression goes to 0. In the denominator here we'll have 1 and 0, and this is 1 and 0. Correspondingly, this expression can be simplified to r sub u dotted with r sub u. And something similar can be concluded for this term here. The numerator will be r sub v times 1. This expression will go to 0. The denominator will have 0 and 1 in this row matrix, 0 and 1 in this column vector. The multiplication here will result in the dot product r sub v dotted with r sub v within the square root sign. And of course, two curves are orthogonal or perpendicular to each other if the cosine of the angle between them at the intersection point is 0. That is, if this dot product is 0. Let me spell this out for you. Partial r over partial u times du over dt1 plus partial r over partial v times dv over dt1 dotted with partial r over partial u times du over dt2 plus partial r over partial v times dv over dt2. You can do your algebra, simplify your result to get g11 du over dt1 times du over dt2 plus g12. Note that g12 and g21 are the same, and g12 and g21 are actually ru dotted with rv. Here we have du over dt1 times dv over dt2 plus du over dt2 times dv over dt1 plus g22, which is rv dotted with rv, times dv over dt1 times dv over dt2. This is a general expression. Here we are not assuming that u is t1 and v is t2. For the two curves to be orthogonal, this dot product between the two tangents has to be equal to 0. Now let's try to compute the area of a surface patch. So let's draw the bounding curves. This is u equals u sub 0 and u equals u sub 0 plus du. This bounding curve corresponds to v equals v sub 0, and this one here is v equals v sub 0 plus dv. Let's say this point is the position vector r at u equals u sub 0 and v equals v sub 0, the values of the two parameters. This point here will correspond to r of u sub 0 plus du and v sub 0, and this point here will be r of u sub 0 v sub 0 plus dv. This vector here is given by r sub u times du. R sub u is partial r over partial u. This vector here is given by r sub v times dv. Notice that this patch is very small in size, it's infinitesimal in size, so Taylor series expansion is allowed. The area of this patch is given by dA, which is equal to the absolute value of the cross product between these two vectors, r sub u times du crossed with r sub v times dv. These are positive scalars, so we can extract them out of this absolute value sign. So we have the absolute value of r sub u crossed with r sub v times du dv. If you would have realized from our previous discussion, the absolute value of the cross product between Ru and Rv is the determinant of the first fundamental matrix G. And of course, with the square root sign. So I can write dA as square root of G11 times G22 minus G12 square. And outside the square root sign, we have du times dv. As I said, this expression here is the determinant of the first fundamental matrix, right here. So if I want to compute the area of the entire surface patch, I'll have to integrate over the entire domain, that is, over the values, permissible values of u and v. So A will be integration over the domain of dA, which is within the square root sign, determinant of g times outside the square root sign du dv. You would also realize that it is the positive definiteness, or in this case in particular, the second principal minor of g, which is greater than 0, that allows the computation of the area of the surface patch. Now let's discuss the relation between the surface and the tangent plane. Let's say we have the surface, we have a point on this patch, let's call it P, and we have a tangent plane passing through P. This tangent plane may or may not intersect with this surface patch. Let's try to figure the conditions for which this plane will simply be a plane or tangent plane to the surface, or it may or may not intersect with the surface patch. Let's plot another point on the surface and call it R. So this is vector PR. This vector here is normal to the tangent plane. Let's call it N. This distance d here can be seen as the projection of PR on this normal N. So if at P the position vector is R u0 v0, which is this point here, and if at R the position vector is R u0 plus du v0 plus dv, then PR is given by the position vector of R minus the position vector of P. D is the projection of PR on this normal. So D is the dot product between PR and N. Since du and dv are small, we can use Taylor series expansion. So this projection D can be approximated as partial R over partial u times du plus partial R over partial v times dv plus partial 2R over partial u partial v times du dv. This corresponds to the mixed derivative plus half of partial 2R over partial u squared times du squared plus half of partial 2R over partial v squared dv squared. If If you're wondering, this expression is the expansion, the Taylor series expansion up to second order terms. And of course, we have dotted within here. Let's try to simplify. So this expression on the right hand side is equal to r sub u dotted within. So this expression is r u times du plus r sub v, this here, dotted within, times dv plus partial 2r over partial u partial v dotted with n du dv plus half of partial 2r over partial u squared dotted with n du squared plus half partial 2r over partial v squared dotted with n times dv squared. Let's try to simplify this expression a little further. Just in case if you have missed the previous construction, we have the surface patch, we have a point on it, P. Through this point passes a tangent plane. We have another point, R, on the surface patch. We construct a vector PR. We let a normal n pass through point P, and this normal n is perpendicular to this tangent plane, and we are trying to compute the projection of PR on this normal n here. Now you would note that n is perpendicular to the tangent plane, because of which r u dotted with n is 0, and also r sub v dotted with n is 0. Recall from before that the vectors r sub u and r sub v in fact define the tangent plane. So what will happen to this expression? Since this dot product is 0 and this dot product is also 0, we have d equals partial 2r over partial u partial v dotted with n du dv plus half of partial 2r over partial u squared dotted with n du squared plus half of partial 2r over partial v squared dotted with n dv squared. And we can express this right hand side in the matrix form as half of this row vector du dv times some matrix, we'll come to that in a while, times the column vector du dv. Coming back to this 2 by 2 matrix, the constituents are r uu dotted with n, r uv dotted with n, r uv dotted with n, r vv dotted with n. This is the second derivative of r with respect to u, mixed second derivative of r with respect to u and v, the same here, and the second derivative of r with respect to parameter v. This matrix here has a name. It is called the second fundamental matrix and is represented by bold D. This matrix allows us to classify points on the surface patch. Let's work towards that. So we have 2D equals the row matrix du dv times this 2 by 2 matrix, the second fundamental matrix D times the column vector du dv. In algebraic form, this is r uu dotted with n du squared plus 2 r uv dotted with n du dv plus r vv dotted with n dv squared. Let's give some names to these dot products. So r uu dotted with m, let's say it's L. R uv dotted with n is m, and r vv dotted with n is n. I just said that. L, m, and n can be called as the second fundamental form coefficients. So the second fundamental matrix D is written as L, m, m, and n, which is r uu dotted with n, r uv dotted with n, r uv dotted with n, and r vv dotted with n. Now, what is the normal? In terms of the partial derivatives of r with respect to u and with respect to v, we know this from before. The unit normal is the cross product between r sub u and r sub v over the absolute value of this numerator here, which is equal to ru crossed with rv over the square root of the determinant of the first fundamental matrix G11 G22 minus G12 squared. So if we use this result here, we get the second fundamental matrix D as 1 over the square root of the determinant of G times r uu dotted with ru crossed rv, r uv dotted with ru crossed rv, the same element here, and r vv dotted with ru crossed with rv. So these are scalar products. So given a surface patch as a function of two parameters u and v, you can compute both the first fundamental matrix G and the second fundamental matrix D. This is straightforward. The second partial derivative of r with respect to u is x uu times I plus y uu times j plus z uu times k. I, j, k are unit vectors along the x, y, and z Cartesian coordinates. Likewise, you can compute the mixed second derivative and the second derivative with respect to parameter v. X, y, and z are scalar fields along the x, y, and z coordinates. You can do this. Ru crossed with Rv is I, j, k, xu, yu, zu, xv, yv, zv, the determinant of this 3 by 3 matrix. So the second fundamental form is equal to 1 over the square root of a squared plus b squared plus c squared. And then we have 2 by 2 matrix here with elements d11, d12, d21, and d22. A is yu times zv minus yv times zu. B is z sub u x sub v minus z sub v x sub u, and C is x sub u y sub v minus x v y u. D11 is the determinant of this 3 by 3 matrix x uu y uu z uu x u y u z u x v y v z v. D12 is the same as D21, which is the determinant of the second 3 by 3 matrix x uv y uv z uv x u y u z u x v y v z v. And of course, the fourth element D22 here is the determinant of x vv y vv z vv x u y u z u x v y v z v. So in a sense, if the surface patch is given as a function of u and v, as I said before, the second fundamental form can be computed using this algebra. Let's classify some points on the surface now based on this, based on the second fundamental form. Let's start with the projection of a position, rather a free vector PR, where P and R are 2 points on a surface patch, and through P a tangent plane passes. So D is equal to half of L du squared plus 2m du dv plus n dv squared. So if a tangent plane would intersect a surface, it would do so at all points where d is 0. That would mean that L du squared plus 2m du dv plus n dv squared is equal to 0. So this is a quadratic equation in both du and dv. So I can solve du in terms of dv, and the result is minus m plus minus the square root sign m squared minus ln over L. Of course, depending on how this expression behaves, m squared minus ln will have no one or multiple solutions. Case 1, we don't have any real value of du, which implies that we do not have any point on the surface through which the intersection plane or the tangent plane passes. P is the only common point between the tangent plane and the surface, and there is no other point of intersection. So that point is called the elliptical point. Case 2. If m squared minus ln is equal to 0, we have L squared plus m squared plus n squared is greater than 0. So du is given by minus of m over L times dv. I can write du as u minus u0, and I can write dv as v minus v0, where, if you recall, point P was the position vector corresponding to parameter values u sub 0 and v sub 0. So this expression here is u minus u0 equals minus of m over L times v minus v0. Physically, the tangent plane would intersect the surface along this straight line, this one. These points are termed as parabolic points. Case 3. We have m squared minus ln is strictly greater than 0. We'll have two real roots for du. And so the tangent plane at point P will intersect the surface patch along two lines passing through P. So we are talking about hyperbolic points here. Finally, case 4, where L is equal to m is equal to n, which is equal to 0. The point P is called